Good morning everyone, I'm Terje and today I will show you how you can do modal analysis in NX SOL103. This solver can do response type of analysis as well, but in this video I will show how you can run modal analysis and study free vibrations of a loudspeaker. And I will use a Bowers-Wilkinson DM602 loudspeaker as an example. And this model has been reversed engineered by a good friend of mine, Magnus Skogsfjord, which is posting a lot of really good NX design videos on YouTube. He also has nxportalen.com, which I strongly recommend you to check out. In this video, I will show you how you can use eigenvectors, mode shapes, in order to improve the structural design of the loudspeaker, and how you can check the eigenfrequencies and compare them with certain excitation frequencies in order to optimize the structural design. And of course, I will show you how to set up and run this analysis. My idea here is to customize this loudspeaker to avoid resonances when playing power chords. And then I think about the lower E and A string. And those two strings, resonant, they vibrate at 82.4 Hz and 110 Hz. And the basic idea here is to avoid structural resonances in this frequency range and close to them as well. I will assume the following fake properties because neither Magnus or me know the exact properties of this loudspeaker. We don't know the wood and the mass of each element, so we just do some guessing. The initial model has a total mass of roughly 9 kilos, which I think is 1 kilo below the actual loudspeaker. And in order to simplify the analysis, I use polyethylene material, isotropic. Of course, the real loudspeaker has not isotropic materials. And I assume an E modulus of 1000 megapascal, a Poisson ratio of 0.4. And then I guess that the tweeter element weighs roughly 0.5 kilos. And the base element weighs 2 kilos. Base port mass, that means the plastic part in front, well, I guess it's about 0.2 kilos. And the same speaker connector mass at the rear of the loudspeaker, roughly 0.2 kilos. So let's make a DM602 Vai Edition. This is the loudspeaker, and I guess it's a rather good representation of the real Bowers-Wilkinson loudspeaker. I know Magnus is really paying attention to the details here. However, some of these details have to be removed, and typically the front pattern here has to go, and we also have to delete all the small faces, the blend faces, in order to create a decent mesh. And you can also replace these faces here with these faces in order to simplify the model. And also these elements are not correctly modeled, I guess, so they can just be hidden or removed. And you need to find a good way to represent them in a finite element model in an easy way. I have a video which shows how you can idealize geometry. It's on this playlist, so please check it out. And then you know how to idealize this loudspeaker. Now we're going to the next step and look at the finite element model. Here is the finite element model. And as you can see, I meshed the cabinet and the front independently. So I have two separate meshes here. And I've used an average element size of 10 millimeters, and I used C-tetra 10 elements for the mesh. In order to connect these two meshes, I've used an mesh mating condition of type glue coincident to actually merge these two meshes. And as you can see, they are glued together here. You can see that the nodes are connected, or the elements are connected. And if I did a check, you can see there are no coincident nodes between these two surfaces. Then, in order to represent the loudspeaker elements, I've chosen to use RB2 elements. So typically here you have the RB2 element for the base element, Of course, RB2s are infinite stiff, so it's not fully correct, but this is a demo, and I do it the simple way. In the center of these RB2 elements, I'm using 0D elements. And for example, for the big element, the base element, I have a concentrated mass 2 in the center of the RB2. And I've applied a mass of 2 kilos in this location. And I did the same for the other concentrated masses here. There is a concentrated masses representing the tweeter, and I've given it a weight of 0.5 kilos. And then the base port here, it has a concentrated mass of 0.2 kilos. And the last one is here, the backside. It has a mass of 0.2 kilos. So this is my finite element model. It's connected, and it has RB2 elements with concentrated mass elements in the center, representing the loudspeaker elements. So let's see how we can do a modal analysis of this initial design. Now I'm in the pre and post task, and I've created a sim file. And then I want to create a solution, new solution. And I want to create a flexible, not a flexible body solution, a real eigenvalue solution. You see, we have different SOL103 options here, like response dynamics. But in this case, I don't want to apply excitations or loads. I just want to do a real eigenvalue analysis. And the default setup is that I will get 10 number of modes, or 10 modes, but I think I will request 12 in this model. Okay. And then automatically a subcase is created, and I actually have to select my launcher setup from here. I think it's this one. Let's check. 12, yes. I don't want to apply any kind of constraints because I don't know where I want to put this loudspeaker. I could bolt it on the wall or glue it to a table, but I think it would be quite free, and that's why I don't want to apply any artificial constraints. I will study the free vibrations without any constraints and no loads. So then all I have to do is to run the simulation. Solve. Then after a few minutes, the solver has completed. Let's just check the numerics, sparse matrix solver, and then it has to do a vector iteration process in order to calculate the eigenvalues and the mode shapes. There we are. I've completed the simulation, and no errors and warnings. So I just want to check the results then. Here I first get 6 modes, which are of practically no interest because those are rigid body modes. That means since I have no constraints, there is no stiffness against rigid body motion. That means the loudspeaker is able to move in X, Y, Z direction and rotate around those 3 axes without any kind of stiffness. That's why we call them rigid body modes. It's not that the model is rigid, it's just that the model is not constrained. And this can be used as a check. If you get like 12 rigid body modes here on this model, you probably have forgotten to glue or connect the 2 meshes. And then you will get 6 rigid body modes for each mesh, the front and the cabinet. So that's a good check on your finite element model, if it's good or not. But let's check the first mode. It's mode number 7. And let's animate it. Here's the mode shape. And we see that the side walls are bending and the front wall as well. And then we can see that the eigenfrequency is 71 Hertz, roughly. That means that the lower E string, the E2 string of the guitar, might cause a resonance in this cabinet because it has an excitation frequency of 82 Hz. So we probably want to change or reinforce the loudspeaker in order to get rid of this mode shape. And if we want to increase this eigenfrequency, we can reinforce the loudspeaker where you have the largest displacements here. And remember, this is just a scaled eigenvector. It's normalized, so this doesn't say anything about if this mode shape is actually being excited. It might not, but since the E string is quite close to this eigenfrequency, we should do something to avoid that risk. Let's check out the next mode. It's mode number 8, and it has an eigenfrequency of 93 Hz, which is in between E2 and the A2 string. And it's a quite local displacement around this tweeter. So it's mainly the front panel which has to be reinforced to increase this resonance frequency, the 93 eigenfrequency. And then we should probably try to stiffen it so that it exceeds from 93 to above 110, which is the A2 string. Let's check the next mode. It has an eigenfrequency of 114 Hz, which is quite coincident with the A2 string in the power chord. So I think we should make sure that both the rear wall and the front wall is reinforced. The question is how you do it, because you have to reinforce the front and rear wall so that the stiffness and mass ratio increases, because if you add too much mass, you have no effect really. But we see that we have at least 3 eigenfrequency here, which is important. Let's check the next one. It's mode number 10. That means the fourth flexible mode. It has a resonance frequency of 119 Hz. It's above the E2 string, so it's not likely that it will resonate, but it might do it, and we should make sure that this one also is increased. And that means we have to increase the side walls. But then again, that's the same conclusion and the same thing we had to do in order to increase the first resonance frequency of roughly 71 Hz. So if we reinforce the side walls, we will increase the eigenfrequency number 7 and 10 in the same run. And if we reinforce the front and rear wall, we will increase the other eigenfrequencies. Then let's check mode number 11. We see it's also a deflection of the side walls, but here we see that the resonance frequency is 137 Hz. And that means it's not likely that power chords will interfere with this resonance or this eigenfrequency. So just to wrap out, we have to check out the mode shapes in order to know where to reinforce the structure in order to increase the corresponding eigenfrequencies. And now, let's see how we can do it. Now I have moved back to my master model and I'm in my part file. And what I've done is I've added a few ribs because I think these ribs will strengthen or stiffen my cabinet quite much without adding too much mass. And what I've done is to join these new solids with the original cabinet. So that means I have the same solid, and when I then open the FEM file, it will remesh itself when you update it, and then you don't have to use more glue commands because we have mainly the same, from a topology view, we have the same geometry. So let's go to the application, pre and post, and then we open the FEM file, display FEM. And we have to remesh it. Update. That's it. We can now see that we have, if we go to view, clip through, edit section, we see that the mesh has adopted the new geometry. So then we are ready to run a new modal analysis. We use the same simulation file and we run it once more. Solve. Okay. Then the simulation has completed and I want to check if my design changes have been successful or not. First we have the 6 rigid body modes, which are of no interest, and then let's have a look at mode number 7, which is the first flexible mode. Let's first check the frequency. It has increased from 70 to 100 Hertz, which is good. We can see the mode shape here, that actually the inner rib, which I designed, still is vibrating, and perhaps we need to make it even stiffer in order to increase the frequency from 100 and to above the A2 string. Because now we have no resonance problems due to the E string, which has a vibration frequency of 82. It's lower than the lowest mode, so that's good. But the A2 string is still vibrating with 110 Hertz, and it can initiate resonances with this mode number 7. Let's quickly check out the next mode. It's mode number 8. It has a resonance frequency of eigenfrequency of 113 Hertz, which is quite close to the A string. We probably have to reinforce this area around the tweeter in order to get rid of this one. Let's check the next one. It's mode number 9, and it has an eigenfrequency of 140 Hertz, 46 Hertz, which is well above all power chords. So we don't have to care about this one. But we still have to do some design modifications to play power chords without any risk of resonance problems. Then we're back to the master model, and I made a few changes. Let's view it as in section view. I've thickened the ribs with 5 millimeters, and I've made them taller, 10 millimeters taller, and that should increase the stiffness quite much without adding too much mass. That means increasing the overall stiffness to mass ratio. So that's the only modifications, and then I can display the FEM model, and I update it. I don't have to add any more gluing commands here. We can see, well, actually I do, because we can see that the mesh here is not coincident anymore. That means I have to apply mesh mating conditions for the geometry once more, and then remesh it. And now you can see that the nodes are coincident. Well, there are no coincident nodes, but the meshes are aligned and connected. And that eliminates my unwanted rigid body modes. I only have 6 of them now. So then the FEM model is updated, unless I want to do something with the tweeter. And there was one resonance frequency that was still too low, which based on the mode shape told me that I have to strengthen this area or reduce the mass. And let's hope that it's enough to reduce the mass, and imagine that we can find a tweeter which is not that heavy. The first one was 0.5 kilo. Let's say that we can find one which is 0.3 kilos. Okay. So then, you know, there are 2 ways of increasing the eigenfrequencies. You can increase the stiffness or reduce the mass. And then we go to the solver, the sim file, and we run the simulation once more. And let's see what the results are. Then the solver has completed, And we want to check if we have been able to move the resonance frequencies away from the excitation range of the E and the A string. And that range was between 82 and 110 Hz. That means we don't want any eigenfrequencies to act below 110 Hz. So let's check. Let's go to mode number 7. And here we see that we have been able to increase the eigenfrequency from roughly 113-14 Hz, I think, to 130. And now we have the lowest eigenfrequency well above the excitation range of the power chord. That means both the E and the A string. And that's a great achievement. And you can see from the mode shape that the sidewalls are not moving that much because we have stiffened the ribs without adding too much mass. Then we can go to the next mode and check it. And we see that this mode shape is mainly located in the tweeter area, and also some displacement on the backside. The eigenfrequency related to this mode shape has increased very much because we almost we lowered the mass of the tweeter quite much, from 0.5 to 0.3 kilos, which has a major effect on this eigenfrequency. And it's well above the excitation range of the power chords. That means that based on a few design iterations and the SOL103 solver, we have been successfully able to design a Steve Vai Edition of the Boris Wilkinson loudspeaker. And I guess that means we are ready to play power chords.